Hello again. Can you remember last lesson we were looking at the relationship between uh, electricity and magnetism? Well, today follows the same theme. We'll be looking at light. Light is shortwave radiation, which is an electromagnetic wave. Um, why are we studying light? Well, we're studying light because this is how the Earth receives its energy from the sun. It receives its energy from the sun through light, electromagnetic waves, shortwave radiation. Okay, if we look at this top graph here, is going to represent an electric field. Now, to make an electric field, we need to change the charge here. So there's a positive charge and a negative charge. And you need to actually change the charge. So this can start off as a positive charge, okay? And then it'll become a negative charge, then a positive charge, okay? So in fact, these are sort of alternating. They're sort of changing from one to another. So let's start off with a positive charge. Oh, this is time, by the way. Time is this way, right? It can be the same with time. Time will be this way, right? So let's start off with a positive charge. And let's see. Oops, not very good at drawing here, but let's see what we can do. Okay, now I should really be trying to draw a sine wave here. Okay, something like this. That's 1, 2. That's 2 waves. Yes. Okay. So this here now is an electric field because we were changing the charge here. Yeah, it was changing from positive to negative, from negative to positive, and this is producing an electric field, which is traveling out through space, or traveling. Yeah, just traveling through space, really. Now this electrical field will actually create a magnetic field. But let's look at how the magnetic field will be created. If we look at this point here, even though there is a maximum amount of positive charge, there's very little change in charge. Yes, there's the sort of the line is sort of level here, isn't it? It's a whoops, well, that's not a very good line. It's a draw a better line. The line is level, isn't it? It's because the line is level, there's no change in electric charge. Whereas at this, well, around this region here, right, this is where there is maximum change in electric charge. So let's draw all the points where there's maximum change in electric charge. There's maximum change in electric charge here. There's maximum change in electric charge here. Maximum change in electric charge here. Yeah? And maximum change in electric charge there. Right? Let's just draw the points where there's minimum change in electric charge, right? So even though we have a lot of charge here, but the actual change in charge here, right, happens very slowly here. And the change in charge here happens very slowly here, and the change in charge happens very slowly here. So let's now plot these points here on the magnetic field graph. Right? So point there, and a point there. Okay, so let's start off with here. So here we've got very little change in electric field, which is going to result in 0 magnetic field. Put that point there. Right? Now here we're getting the maximum change. Remember, I'm talking about the change of the electric field, not the electric field itself, but the change in electric field. It's changing from positive to negative at its fastest point here. So let's draw a line down here, and let's call that a point just there. Right? Now down here again, the actual change in the electric field is very slow, right? Which causes minimum magnetic field. Here, the change in electric field is very fast, yeah. So we get maximum magnetic field. But notice it's the other way this time. Here it was changing from positive to negative. Here it's changing from negative to positive, which actually gives a different polarity. Yes, this is north here, this is south down here. Okay, up here the actual change, yeah, is the change of the electric field is 0, right? So therefore the magnetic field is going to be 0. This point here. Here maximum change here. Minimum change here. And maximum change there. Okay, so let's draw the new line now through these points. Oops, did that wrong. Okay, something like that. So let's compare these two waves. When the electric wave is at its maximum, the magnetic wave it is at its minimum. So another way to look at this is the magnetic wave is a little bit ahead of the electric wave. In fact, we could actually say it's 90 degrees ahead, yes. That would be one way of looking at it. Another way to explain that we could say that the electric field is out of phase from the magnetic field. Right? Can you see that? Okay, let's take this point here. When the electric field is at its maximum, the magnetic field is at its minimum. So they're sort of out of phase a little bit. Yeah? And this actually produces quite an interesting effect, because now if we look at the magnetic wave, let's look at the points where the change in magnetic field is the most. So the changing magnetic field is the most here. The change in magnetic field is the most here. The change in magnetic field is the most here. And the change in magnetic field is the most here. Let's look at the points where the change in magnetic field is the least. Yeah? So the change in magnetic field here is very little changing magnetic field just here, very little changing magnetic field here, very little changing magnetic field just here, and very little change in magnetic field just here. So let's mark the points where there's very little change in magnetic field. Right. Now this is quite interesting, because now the magnetic field is going to have an effect on the electric field. Yeah? A changing magnetic field will create an electric field. But let's see which way it changes the electric field. Right? So if we look at this point here, there's maximum change in the magnetic field, which is going to produce more electric field. So the electric field is actually going to be pulled downwards like this. Right? Now if we go here, just at this point here, where there's also a maximum amount of magnetic field here, that's going to have an effect on the electric field, and it's going to sort of reinforce, it's going to make the electric field even stronger. It's going to sort of try and pull it up that way. So from this, we can see that the electric field creates a magnetic field, and then the magnetic field itself actually makes the electric field stronger. And because the electric field becomes stronger, then the magnetic field becomes stronger. Right? So this is what keeps the electromagnetic wave propagating. This is what keeps it, so it just doesn't completely fall down and collapse. Right? So there's a similarity really between an electromagnetic wave like light and a surface wave like the sea waves. Now, if you remember the sea waves, let's draw a sea wave here. The sea waves, as we said, were made up of circles, didn't we? If this is the sea waves, the sea waves, and I said that we had these, sort of circular motion. You can probably remember I drew the circles, didn't I? Something like this, okay? And I said that the actual water was moving around. The water was actually moving around in circles, like this, okay? Right? Even though the wave was moving forward like this. Okay. So the wave's moving forward like this, and the sea waves are moving this direction, but the actual water is moving around and round. Right? So you can sort of see that there's a sort of similarity here. Yeah. Now, if this circular motion stopped, the waves would stop as well. Yeah? And if there wasn't this relationship going on between the magnetic field and the electric field, well, the light wouldn't go very far either. Okay, the light wave would also collapse. So it's this relationship between the magnetic field and the electric field which keeps the light wave going, which keeps it propagating. Okay, I hope that's sort of clear to you, and I'll see you next lesson. Bye.